Hi everybody, welcome to my kitchen in this crazy time that we have going on. For this coming week, the next thing that we're going to be talking about is momentum and collisions. Momentum is basically like, like when you get moving and let's say you're skating along and like on a roller skates or on a skateboard and you take your foot up and you just coast, that has to do with momentum. If you're going down a hill, down one side and then going back up the other side, what actually keeps you going and moves it, that all has to do with momentum as well. So I wanted to go ahead and cover the momentum. There's some practice problems along the way. I'll try and make this as quick as possible. I don't want an hour-long video, so so we'll go ahead and we'll get started. The first part that we'll talk about is momentum and impulse. When a soccer player headbutts a moving ball, the ball's velocity changes very rapidly. First of all, remember that velocity is a vector, so the direction is part of the velocity. So when the ball is coming in and the person headbutts it, it changes direction and it has a velocity to it. It's going from this to a negative, a positive to a negative. As it hits your head, it's coming in at positive, it shoots off at the negative velocity. So there's a huge change in velocity that takes place during that little headbutt. The quantities and the kinematic equations describe one-dimensional motion, predict this motion after the collision. We've done kinematics, we've done a lot of those kinds of things. So we'll be using some of those for for some of the problems that we'll be working. Newton's laws also can be used to describe the change in motion, because remember Newton's third law is every action has an equal and opposite reaction. The first formula that I want to give you guys is the formula for momentum. The sign for momentum is kind of crazy. It's actually the Greek letter rho. It kind of looks like a P, just like that. So that's rho. So that's momentum is equal to mass times velocity. Okay? So that's the formula that we're going to be using. The units for momentum are kilogram, meters per second. So that's the unit that we're going to use for momentum. Okay? Now if you consider two bowling lanes, down one bowling lane you roll a ball that's a bowling ball. And down another lane you roll a dodgeball ball. Now of course both of the balls could be about the same size, but the bowling ball is going to have more mass. And because of the more mass, it's going to have a greater momentum, as long as they're traveling at the same velocity. So the greater the mass at a same velocity, the greater the momentum is going to be for that particular ball that's going. A small object can have just as much momentum as a large object. It just has to have a much greater velocity. So for example, if you had a small mass, let's say 10 kilograms times, let's say 10 meters per second, that's going to be 100 kilogram meters per second. But if we had a smaller mass, let's say 2 times 50 meters per second, that's also 100. So both of these objects, even though they have different masses, they're going to have the same momentum if they have different velocities. That makes sense. Simple multiplication right there. All right, so here we have a couple practice problems. If you want to give it a shot, the problems a shot, the first one is a deer with a mass of 146 kilograms. So I have a mass of 146 kilograms is running head-on toward you with the speed of 17 meters per second. Find the momentum of the deer. I'll give you a second if you want to pause the video while you work that out. There we go. 2,482 kilogram meters per second. All right. The second problem. A 21 kilogram child on a 5.9 kilogram bike is riding with a velocity of 4.5 meters per second to the northwest. What is the total momentum of the child and the bike together? What is the momentum of just the child? What is the momentum of just the bike? So it's the same problem, just 3 different times. Okay? And what do you have to do for the first one though? For the bike and the child together? That's right, you have to add the masses together. So I have mass of child, mass of bike, there we go. So the formula we're going to use, rho is equal to mass times, mass times velocity. There we go. Yeah. All right. The first one was, what was the mass of the child and the bike? So I have to add these two together. That's for the child and the bike. There we go. The momentum, this is going to be the momentum, what it needs to be for next. The child. Child, 94.5, and the momentum of the bike, that's the bike. Alright, there we go. That's the first one. There's our first practice problems. And just real quick, just so you can see the difference between the answers that are on the slide versus the answers that I have here. Remember, the answers that I have on the slide are all rounded off with significant figures. So that's why there's a little bit of a difference. Like this actually says 27, that kind of thing. Okay. Now a change in momentum can change, of course. If the velocity changes or if pieces fly off of a car, then you can possibly have a change in momentum. So a change in momentum takes some sort of force and some amount of time. It depends on how strong the force is and how long the contact is. Like for example, if you have like in the picture, there's racquetball players. If you take the racket and you hit it and you just bump it, you're going to have one result. But if you take it and you actually swing and you follow through with it, then you're actually going to have a different reaction. You could have a different velocity when it comes off, when the racquetball comes off of your racket. He would need to exert less force on a slow-moving ball than on a fast-moving ball. okay? And just if you catch a fast-moving ball with your bare hands, it will sting, while a slow-moving ball would cause no discomfort whatsoever. That's the whole thing of, like, let's just say you're standing there and you're a catcher and you're trying to catch the ball coming at you, and someone throws that ball at you. If you just stand there and hold your hand like this, it's going to hit you and it's going to hurt. But what if you actually, as the ball starts to come into your mitt, you actually back off like this and take this much time to slow that ball down? It's going to hurt a lot less. Okay? On the next slide, we have our relationship between force, momentum, and time. Force, here's your next equation. Force is equal to the change in momentum, oops, it's rho, not p, over change in time. And another way to kind of work that through is actually if we multiply both sides by time, we end up that with force times change in time is equal to our change in momentum. Okay? Same formula, just written in two different ways. Now, with the change in momentum, remember whenever we have a change in, it's always final minus initial. And if we think about what the formula for momentum is mass times velocity. So let's just take it one step further and say this is velocity final minus mass times velocity initial. And this is my change in momentum. Okay? Now this formula that we have right here, we know that as the force impulse theorem, okay? The impulse momentum theorem. This part right here is the impulse. The force times delta t, the force times change in time. That right there is my impulse. And the impulse is just basically how much of a force for how much of a time are you actually going to act on an object. I know I go to my Star Trek days with this because they talk about impulse engines. And impulse engines are just used for guidance and moving things and like this kind of thing, not for real long distances. So if they just need to like real quick change course, they hit their impulse engines just to nudge the ship one way or the direction, up or down, whatever like that. Okay. Now this here also explains why it's very, very important if you're an athlete and you do anything like soccer, basketball, baseball, anything like that, tennis, racquetball, why it's very important to follow through when you take your swing, or when you even with golf, when you take your swing or you're throwing or you're hitting the ball, things like that. The reason is the greater the time that you have, the greater the change in momentum is going to be. So if it comes in at one speed, if you take a minute to really push that force through it, you're actually going to get it to take off at a greater force than if you just pap it real quick, okay? And that sounds kind of funny, I don't know. I'm doing what I can here. Okay, so using this formula right here, we have a couple of problems to solve. The first one is talking about a half a kilogram, a 0.50 kilogram football thrown with a velocity of 15 meters per second to the right. A stationary receiver catches the ball and brings it to rest in 0.020 seconds. What is the force exerted on the ball by the receiver? Okay. So if you need to pause the video, please feel free. All right, so we have the mass is 0.50 kilograms, has a velocity initial of 15 meters per second. The change in time that the receiver uses is 0.020 seconds, and I need to find the force. All right. All right. Now with this one, the one thing that we can think of, like with our change in momentum, we know the final. Okay, we know the final. The final momentum final is going to be 0. The reason is because it's going to come to a stop. they're actually catching it and it's going to stop. Okay? So then if we do this times the initial momentum, mass times velocity, so wouldn't that be, let's see, momentum initial, wouldn't that be 7.5 kilogram meters per second, 0.5 times 15? Okay, so here I have my initial momentum, my final momentum. So my change in initial, or my change in momentum is going to be a final minus initial. So my change in momentum is going to equal negative 7.5 kilogram meters per second. Okay, so then I have, I'll change colors real quick. Whoop. I don't know the force. I'm looking for that. I'm going to go ahead and rearrange this. I'm going to divide both sides by delta t. So I'm going to have the negative 7.5 kilogram meters per second divided by the time, which was 0.020. Okay? And when I divide this, my force is going to equal negative 375 newtons. Okay? Now, why does the negative make sense? Okay? The reason is because the negative, it's actually going to be applied in the direction opposite the force of the ball. Okay? So that's why the negative there. Now, with the problem that it actually says, it says, the answer, it says to the left. All right? The football was thrown to the right, the force is acting to the left. That's why it's either negative or it could be, you could say it to the right. Or to the left, I'm sorry. Okay? All right, next problem. An 82 kilogram man, let me get rid of this. I could have left a bunch of that. Oh well. Alright, so I have the mass is 82 kilograms. He is 3 meters above the surface of the water. Okay, so change in y is 3.0 meters. And comes to rest 0.055 seconds after reaching the water. Alright, and I'm looking for the force. Okay, now with this one, if you think about it, oof, right? I don't have an initial velocity, but do I have a way of finding it? I do. I know that basically he has jumped off of the diving board and he has fallen for 3 meters. I can use my kinematics to find out the formula there, okay? All right, so I'm going to grab my, my handy-dandy equation sheet, and I need to know my velocity initial. Let's see. All right, so I think I'm going to have to use this one. V sub f squared equals v sub I squared plus 2a delta x. All right, I know my initial velocity is going to be 0, so that's just going to drop out. So my velocity final squared is going to equal 2 times gravity, 9.8 meters per second squared, times my change in position, which is 3 meters. Okay, let me go ahead and crunch that real quick. 2 times 9.8 times 3 gives me 58.8 meters per second, or meters squared per second squared. Now what I need to do is I need to find the actual velocity, finish it off, square roots on both sides, and I get 7.67 0.07 meters per second. Okay, so my velocity initial is 7.67 meters per second. That's my initial. My final is 0 because he's coming to rest. All right, I'm going to get rid of this so I have a little bit of room on my little bitty board. Okay, and I need to find out what the force is. Okay, same thing as I did before. My change in momentum. My momentum final. Oops. My momentum final is going to be 0 kilogram meters per second. I need to find my initial momentum. Mass, which was 82 kilograms, times velocity, 7.67 meters per second. Let me go ahead and calculate that out real quick. 82 times 7.67. I get my initial momentum is 628.94 kilogram meters per second. So I have 628 there. Okay, now I can use this and my other information for this piece right through here. Now I couldn't use this time, the 0.55 seconds, to come up with my initial velocity because that's how long it took him to slow down once he hit the water. I didn't know how long it took him to get from the diving board to the water. Okay, so let's get into this. I need my force. I'm going to go ahead and divide both sides by t. I'm going to have basically what is it, negative 628.94. Because remember that this is final minus initial. The final was 0, the initial is 628, so that's going to give me a negative 628, 0 minus 628. Divided by the time, 0.055 seconds. Okay, let me go ahead and crunch that real quick. 628.94 divided by 0.55, and I end up with a force of negative 1143. Let's say 53 newtons. Oops. All right. Okay. There's the second one, and now for the third one. Do I drop this many things at school? I don't know. Okay, for the next one and the last one on this sheet, on this page, I have a 0.4 kilogram soccer ball approaches a player horizontally. Whoops. Let me do this. So the mass of the soccer ball is 0.4. With a velocity at 18 meters per second. The player strikes the ball and causes it to move in the opposite direction with a velocity of 22 meters per second. What was the impulse delivered to the ball by the player? Okay, now with this real quick, remember that this here, the ball is traveling in this direction. In this one, the ball is traveling in the other direction. So this is going to be a negative 22 meters per second, okay? Because of the fact that it's changed directions, we got to make sure we have the correct sign with that too, okay? And I'm looking for the impulse. All right, so I'm looking for this. Basically, all I need to do is just find the change in momentum, okay? And that's going to be equal to my impulse. All right. So my change in momentum, my momentum initial, my momentum final. All right, so I have the mass, 0.4 kilograms, times my initial velocity, 18 meters per second. I'm going to go ahead and do this one too, 0.4 kilograms. The mass is the same, times negative 22 meters per second. All right, let me go ahead and crunch those real quick. 0.4 times 18, I get 7.2. For the other one, 0.4 times negative 22, I get a negative 8.8. And then it's negative 8.8 minus, oops, I need my units, kilogram meters per second. Kilogram meters per second minus my initial, 7.2 kilogram meters per second. Then I have negative 8.8 minus the positive 7.2, and I end up with negative 16 kilogram meters per second. And once again, the negative sign helps me indicate which direction it's going to be traveling in. All right? All right. How are the sample problems? Not too bad? Good. Good. I hope they were pretty easy. Okay. Now, stopping times and distances also depend on the impulse momentum theorem. For example, an 18-wheeler can do some damage if you get hit by it, but a train can have even more of a damage traveling at the same speed because of the fact that it has more mass and therefore more momentum. Now, this next practice problem that we have, this one right here, is going to require a little bit of kinematics, okay? So we have a 2,500 kilogram car, so we have a mass of 2,500 kilograms. It's traveling north, is slowed down uniformly by an initial, from an initial velocity of 20 meters per second. So my velocity initial is 20 meters per second. By 6,250 Newton braking force. All right. It's negative because it's working in the opposite direction of the motion. Use the impulse momentum theorem to answer the following. Okay. So what is the car's velocity after 2.5 seconds? So let's say I need my final velocity, and my time, my change in time, is 2.5 seconds. All right. I need to find what my final velocity is going to be. Okay. Now, I have everything that I need except for one piece. Okay. I'm going to need to extend this. I know the force. Let me use a different flavor. I know the force. The force was given to me. It was a negative 6250 newtons. Okay, I know that. I also know the time. It was given to me in the problem. 0.25 seconds. Okay. Now, I know most of this. The only thing that I'm missing is the final velocity, right? Of course, I'm going to need to carry this down. So my first one, I know the mass, 2,500 kilograms, but I don't know the final velocity. And remember, these are finals first. Velocity final. Minus, once again, the mass is going to be the same, 2,500 kilograms, times my initial velocity of 20. Oops. Meters per second. All right. So I knew all of these bits and pieces except for my velocity final. Okay. So let me go ahead and start working on this real quick. Okay. And what I have so far is negative 15,625 newton seconds is equal to 2,500 kilograms times velocity final. I still don't know this velocity final yet. Minus 5,000 kilogram meters per second. That's this piece right there. Now I just got to do a little bit of math and that kind of stuff, and yeah, let's do that. All right. So let's see, 15. 625 plus 5,000, 50,000. All right. 34,375 is equal to 2,500 kilograms times velocity final. Divide that by 2,500, 2,500, and I get I don't know where to put that. 13.75 meters per second. There we go. So there's my answer to the first part. What was its final velocity after this? 13.75 meters per second. Okay. I just had to add the 5,000. Oops, is it 5,000 or 50,000? Oops, it's 50,000. Gonna add another zero in there. I didn't have enough zeros. So 50,000. That's 2,500 times. Oops. Where is it? 2,500 times 20 gives me this. Then I had to add it to both sides, and that gave me the 34,375. Then divide by the 2,500, and I get 13.75 meters per second. All right. So there's the final velocity. All right. I'm going to write that down just in case I need it someplace. Velocity final. 1375 meters per second. All right, so that was the first part. Second problem. All right. How far does the car go during the 2.5 seconds? Oh. All right. Where does the car go after during the 2.5 seconds? Okay, for this one, I'm actually going to need my kinematics for this one. Okay, so I'm going to go back to my my equation sheet, and let's see. I need to know how far does it go. I think I'm going to use. I'm going to use this equation. X sub f is equal to x sub I plus v sub I plus v sub f over 2 times time. Oops, that'll work. Now I'll just leave the delta out. Times time, right there. Okay. The initial position, we're going to call that 0. It's just saying how far does it go. So starting at 0, that's going to cancel that out. So my x sub f is equal to, I had to use this one because I didn't have any accelerations or anything, and I didn't want to have to go figure that out. So my initial velocity was 20 meters per second. My final velocity was 13.75 meters per second divided by 2 times the time of 2.5 seconds, right? Yep. All right. So let me go ahead and do this real quick. 33.75 divided by 2 gives me that times 2.5, and I get, what did I do? Hold on. Velocity initial, I got 20 plus 13.75 divided by 2 times 2.5, and I get an x of f of equal to 42.19 meters. All right. Awesome, awesome. All right. And the last problem that we have, how long does it take for the car to come to a complete stop? Nice, right? How long does it take for the car to come to a complete stop? So with this one, I'm going to use, everything to come up with my delta t right there. So I'm going to have to back up a little bit and do some other math. Okay, so I have my, so I know that for my change in momentum, my momentum final is going to be 0. How long does it take to come to a stop? Okay, my momentum initial is the mass, 2,500 kilograms, times the velocity, 20 meters per second. Let me do that. Wasn't that 50,000? Yes. So my initial velocity was 50,000 kilogram meters per second. Okay? So there's my initial momentum. It also told me what the force is. So I know the force, right? I know the force. I now know my change in momentum. It's going to be negative 50,000, right? So all I got to do is solve for time. So it's going to be change in momentum over force, and that's going to equal my change in time, right? My change in momentum, of course, is going to be negative 50,000 kilogram meters per second, divided by the force, which was a negative 6,250 newtons. Do the division on that. Negative 50,000 divided by negative 6,250, and I get a change in time of 8 seconds. All right, there we go. Awesome, let me get rid of this real quick and then we'll move on. All right, moving on. There we go. So impulse momentum theorem. This deals with basically if you extend the force over a longer period of time, it makes it easier for you to do things. Like for example, if you were standing on top of a chair or on top of a table, and you went to jump off of that table, if you were to keep your knees straight when you hit the ground, it's going to hurt. You're going to get jarred all the way through your knees and all the way up through your body, rattle your jaws. But if you jump and as you land, you squat and bend your knees and slow down the amount of time or extend the amount of time that it takes for you to slow down and stop, it's less of a jar on you. Okay, that's the whole thing. Like with like when you play like egg toss and you throw water balloons and stuff like that. You just don't stand there like this and hope the hand lands in your hand. You actually catch it and then cradle it to a stop as you let it, slow it down slowly. So that way it doesn't actually break and crash. If you jump off or if you drop an egg on a pillow, the pillow slows the egg down a lot more than if you just drop it and hit the counter. Kind of interesting too. It's kind of like the like why is it that if you go to the bathroom and you get a piece of toilet paper, if you try to pull it real carefully, it just pulls it off the roll. But if you jerk it off real quick, it rips rips right off there the piece that you need. That has to do with the amount of time that it takes. All right. All right. Okay. Next section, conservation of momentum. So basically, when we've talked about momentum, it is something that is conserved throughout a system. Okay, if you look at if you play pool, you play billiards, and you take your cue stick, you hit the cue ball rolls over, hits the ball, and then the cue ball stops, and then the other ball keeps moving. That's because of the conservation of momentum, okay? However much momentum there is before a collision, the same amount of momentum is going to be there after the collision. It may just look a little bit different because of the different weights and masses of things. Let's see. It looks so. It talks about on this slide. You got a picture of the pool balls and also the bowling ball with the bowling pins. When the cue ball hits that yellow ball in the picture, the momentum is transferred from the cue ball to that yellow ball, which causes the yellow ball to move. If you're bowling and you throw that ball down the alley, when it hits the pins, the momentum is transferred from the bowling ball to the pins. Okay. Ready for another formula? I thought so. All right. The next formula is basically a formula that we've already had, just beefed up some. Okay? So what we're going to say is the mass of object 1 times the velocity of object 1 initial. Okay, this is starting. Plus the mass of object 2 times the velocity of object 2 initial. Okay, so it's just the momentum formula for one object plus the momentum of another object. Okay, and that's going to equal the mass of 1, velocity of 1, final, this is after the collision, plus the mass of 2 times the velocity of 2, final. Okay? So if you think about the two billiard balls, this is my cue ball, this is the yellow ball. And once again, cue ball, yellow ball. So momentum, whatever it is here, has got to equal whatever it is there. Okay? Another way of writing it, I mean, without, kind of condensing it, the momentum of 1 initial plus the momentum of 2 initial is equal to the momentum of 1 final plus the momentum of 2 final. That's all there is to that, okay? So basically we can use these to find out, like, how fast is this ball going to roll after the cue ball hits it. Other things, like scientists can actually use this as far as like with traffic accidents and things like that. If you kind of work backwards with a traffic accident, if you know that that this car here was stopped. Let's say that it happened where there's a car sitting at a red light and another car doesn't see them and rear ends them. Okay, so you've got mass 1 of velocity 1. You can figure out how far did it actually move. What was its velocity after it got hit. Then you can go back and figure out, like, did it do this where the car came in, smashed it, moved it off? And just by using the information from a crash scene, the police officers can actually figure out how fast you were going or the other person was going when they rear-ended the car that was stopped. Kind of gnarly, right? Okay, so let me get rid of all this mess and we'll move on. Okay, so momentum is conserved in collisions. It's conserved when objects push off of each other as well. Like, let's just say, I don't know, let's say you're in you're on an ice skating rink or something, and you and another person are standing together and you push off of each other. You can use the conservation of momentum to figure out how fast each person's going. Two objects that have an initial momentum of 0 and begin moving away from each other. Or in the situations where momentum is conserved, the total momentum after the two push off should equal 0, which basically means, like, whatever the mass times velocity of one, it's going to be negative if they're moving away, and then mass velocity of the other. So let's say, like, let's see, here's my pond. All right, I know how much you miss my wonderful drawings, and I've got two people, two skaters. Got one person here, one person here. Don't judge. Okay, and they've got their ice skates on. Yeah, aren't those great ice skates? And they push off of each other. Okay, this person, I'm going to use a different flavor. This person travels in that direction. This person travels in that direction. Okay, their initial momentum is 0 because neither one of them are moving. And remember, mass times velocity. So altogether, their velocity is going to equal 0. Now, when they push off of each other, this person here, I mean, we can set it up however we want, but let's just say this person over here has the positive velocity, this person has the negative velocity, okay? Let's just say that this person here altogether, let's say he is zooming off, and let's say he has a momentum of 10, let's say 100 kilogram meters per second. So he has a mass of 50 kilograms, and he's traveling at 2 meters per second. 50 times 2 gives me 100. Now on the other side, let's say this guy here, he's smaller, okay? He has a mass of 25, but he zooms off at 4 meters per second. 25 times 4 is also 100, but he's moving in the opposite direction. So it's going to be negative 100 on this side, kilogram meters per second. Now, if you add those together, negative 100 plus positive 100, you still end up with 0, okay? And that's what has to happen. The momentum needs to be the same before as it is after a crash, a collision, push off, anything like that. Now, there's a question on that slide, the very last one right underneath the picture of the kid jumping. It says, when you jump, say your momentum is 60 kilogram meters per second upward, then mustn't the Earth travel downward with the same momentum? But when I jump up and down, I don't notice the Earth moving away from me, okay? Well, the reason is because, well, it kind of does. But remember the parts of momentum. Mass times velocity. The mass of the Earth is so much bigger than yours that, yes, it'd have the same momentum, but the fact is the velocity would be minuscule compared to what you would have because of the mass, okay? If you think about it, you know, if you have a mass of 10 kilograms and the Earth, and I'm just making this up completely, has 100 million kilograms, to get the same momentum, the velocities would have to be incredibly different, okay? So let's just say if you had a velocity of 5, so we're looking at 50 right there. Think of how small the number would have to be in order for you to get 100 million times some number to equal 50, okay? So that's why you don't actually see the Earth moving around when you're jumping up and down on it. Plus, there's a lot of other stuff that's coming into play with that as well. Like there's other people, other things moving around on the Earth, you know, so it kind of, you know, averages all out. All right. Okay, here we go. Practice D. Okay, so here we go. So we have a, let me go ahead and put this formula up here on my board. It's going to be the long one. M1 V1 initial plus M2 V2 initial is equal to M1 V1, final plus M1 V1, M2 V2, sorry, M2 V2 final. All right. All right. Now let's go ahead and get into the problem. If you want to go ahead and pause it for a second while you work the problem, go ahead and do so. Okay, let me get started. Astronaut. All right. 63 kilogram astronaut. So I have mass of astronaut is equal to 63.0 kilograms. Tethered line breaks. The astronaut is able to throw a spare 10 kilogram oxygen tank. So the mass of the tank is 10 kilograms. Okay. With the speed of 12 meters per second. So velocity of the tank is 12 meters per second. Propelling the astronaut back to the shuttle. Assuming the astronaut start from rest with respect to the shuttle, find the astronaut's final speed. So I need velocity of the, oops. I need velocity of the astronaut final, okay? Let's see. Now I want to go through and just kind of make some of these very specific. The masses, of course, are going to stay the same. That's not going to change beginning to end, nothing like that. This velocity of the tank is actually the velocity of final of the tank. Okay, so it's velocity of the tank final. I need the velocity of the astronaut final. Okay, now what are their initial velocities? Okay, the velocity initial of the tank is going to be 0 because the tank and the astronaut are together. The astronaut is going to throw the tank and go in some other direction. Let's see if I can do this real quick. Oh goodness. There's my space shuttle. Okay, and then you've got astronaut floating around out here. And he's got himself a tank. Okay, and they're floating together, all right? Then what happens is the astronaut throws the tank out, away. And then what's going to happen is because he threw it in this direction, the astronaut is going to move in that direction, okay? So we've got to make sure we get our positives and our negatives in the right places. In this case, I'm going to say moving towards the space shuttle is going to be positive. Moving away from the space shuttle is going to be negative, okay? That means that my velocity of the tank final is going to be a negative 12 meters per second, okay? Because it's actually being thrown and traveling away from the space shuttle. Whereas the astronaut is going to end up moving towards the space shuttle, okay? All right, let me give this a shot. Okay, so mass times velocity. So the first part, mass 1 times v1, is going to be 0 for the astronaut. The reason is because his velocity is 0, okay? Plus, for the tank, mass times velocity of the tank is also, excuse me, is also going to be 0. Oops, I forgot my kilogram meters per second. Kilogram meters per second, okay? So on this side of my equation, this is all going to be 0. And just for space, I'm going to erase this, just so I can have a little bit extra space. And I'll change colors too, why not? Okay, so there's 0. That is the total momentum before, because they're not moving relative to the space shuttle, okay? Now, I need to get into all this. Mass 1, this is for the astronaut. The mass was 63.0 kilograms. The velocity, I don't know yet. Okay, that's the velocity final for the astronaut. I don't know that. But I do know the mass of the tank, which is 10 kilograms, times the velocity of the tank, which is, remember, negative 12 kilograms. Okay? Let me go ahead and do that math real quick. 10 times 12 gives me, 10 times a negative 12, I'm sorry, gives me a negative 120. I'm doing this just to conserve some space. Okay? Now I'm going to go ahead and move this from this side to the other. Okay? So now I have the 120 kilogram meters per second is equal to 63 kilograms. That's the mass of the astronaut times the unknown velocity of the astronaut. Let me go ahead and finish this up. So I have 120 divided by 63, and I get 1.90 meters per second is equal to my velocity of the astronaut final. All right. Cool. Next problem has 2 parts to it. Now you do realize that with that astronaut and everything, if we knew how far apart the astronaut was from the space shuttle, we could figure out how long it would take him to get back to the space shuttle. Yeah, so we could just use our kinematics from there. All right, the next one, croquet ball. Croquet's fun. If you ever get to go outside and play that. Each croquet ball in a set has a mass of 50 kilograms, or 0.5 kilograms. Mass is equal to 0.5 kilograms. The green ball traveling at 12 meters per second. So velocity initial of the green ball. 12 meters per second. Strikes the red ball, which is at rest. Velocity initial of the red. Okay, so that's what it's giving us so far. It's giving us the mass of both balls and then the initial velocities. Okay, so then for the first problem, it says that the green ball stops moving after it hits the red ball. Okay, so we're looking for the velocity. We're looking for the velocity final of the red ball. Okay, and in this case, we know the velocity final of the green ball is equal to 0 because it comes to a stop. Now hold on a second. Let's think through this. We could do this by math. Okay, we could do this by math, but think about it. Okay. If when we get started, this one is 0.5 times 12, right? This one is going to be 0 because the ball is at rest. Now what it's saying is this ball is going to be at rest. What is the velocity of this ball? It has to be 12 because there's no other way for that to actually work out. If we know, let me get a different flavor out here. If we know that this is, let's see, 12 times 0.5, that's going to be 6. We know that's 6. This is 0. Then in the problem it says that the green ball stopped. 0. This has to be 6. Okay? So without doing any math on that one at all, I can tell that the velocity final for the red ball is going to be 6. If you don't believe me, you can do the math real quick. Okay? But it just makes sense. 6 plus 0 is equal to 0 plus what? It has to be 6. Okay. Now for the second part of the problem, it says the green ball continues moving after the collision at 2.4 meters per second in the same direction. So now I know the velocity of the green ball after is 9.6. Or nope. That's that's the answer. 2.4. Okay. So I know it's 2.4. What's the velocity of the red ball? Okay. Now in this case, what we have is we have the red ball coming in, or the green ball coming in, striking the red ball, and instead of the green ball stopping, it continues to move in the same direction that it was traveling before. Now that's really important because that means this is not going to be negative. They don't bounce and go away from each other, they bounce and continue off in the same direction. So none of my velocities are going to be negative. Okay? Alright, change my color real quick. Okay, so let me go ahead and do these real quick. I know mass times velocity 1, that's going to be 6. I'm just going to go ahead and do the math just because of my space. So this I have is 6 kilogram meters per second. That's there here. Mass 2 times velocity 2, that's going to be 0 because it's at rest. Oops, kilogram meters per second. Okay, and that's going to equal, let's go ahead and we got to fill it all in. We know it's 0.5 kilograms times my velocity final, and this is for the green ball, 2.4, plus 0.5, this is for the red ball, times velocity final of the red. I don't know that. Okay, I'm going to go ahead and consolidate up what I can. That's going to be 6 is equal to 0.5 times 1.4, or 2.4. So that's going to be 1.2 kilogram meters per second plus 0.5 times velocity final of the red. Okay, now I just got to go ahead and do my math real quick. Subtract that off of both sides, so I'm going to have, what, 4.8 kilogram meters per second is equal to 0.5 kilograms times velocity final of the red ball. Divide that through. Subtract that from both sides. Okay, and then the last thing I have to do, whoops, I can see it, oh. Now I have my 4.8 kilogram meters per second is equal to 0.5 kilograms times this, so I'm going to go ahead, I got to divide both sides by 0.5. Then I end up with 4.8 divided by 0.5, and I end up with 9.6. And that's my velocity final for the red ball. All right? Awesome. Okay. Moving right along. Now, real quick, forces in real collisions. What we've been dealing with here are forces that have been, like when we talk about the impulse and all that, we were talking about forces as being a constant and steady force. The problem is if you're in the real world, that isn't always necessarily true. If you look at this graph right there, you can see it actually shows the way that the forces actually change in the course of one accident. Some of that has to do with what they call crinkle zone or crumple zones. Like your cars, modern cars are actually built to, if you know, in case of a collision, that they actually crinkle in certain places, so that way it's a very controlled type of accident. There is a way of trying to reduce the amount of damage and injury that happens during an accident. So we are talking about them being in constant, you know, this is the force through the entire collision, but that's not necessarily true in the real world. All right. The last little thing that I just want to cover real quick are what we call elastic and inelastic collisions. What we've been dealing with so far are what they call elastic collisions. This formula right here, okay? With elastic collisions, they hit each other, they bounce off, there's no real energy that's lost or anything like that, okay? Okay. Now, in an inelastic collision, what ends up happening is they don't bounce off of each other. So sort of think of it as, I have this ball right here. I have this ball right there. Let's say they're made of clay. This ball is moving in this direction. This ball is moving in that direction. And when they hit, okay, then when they hit, they stick together and travel off in another direction. Now this isn't just like, you know, balls of clay and that kind of stuff. Imagine that you're standing at your front door and you get home from someplace, you open up your front door and you have a big dog, okay? And this big dog is a lover and they miss you so much. And you're standing at the door, you're so happy to be home, and you look, and here comes boom, 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 big dog come traveling at you. And just as they get close to you, they jump up into the air, and they jump into your arms. Aw, isn't that precious? But it's going to knock you and your dog backwards. You're going to stumble a little bit. That's what's happening here. So imagine that this is the dog, and this is you. When the dog jumps into your arms, you travel away. Now what happens is we don't think of it as two separate masses anymore. We think of you and your dog, or these two balls combined, as one mass, okay? The math is pretty much the same. Let's see if this makes sense to you, okay? Oh, let me get rid of this too. Okay, so let's take a look at this formula. This is you. You're standing at the door. Mass 1, velocity 1, initial. You look up and you see your dog. Okay? Mass of the dog times velocity of the dog, initial. Okay? That's going to equal the mass of you plus the mass of the dog times the velocity final. Okay? So basically what happens, the difference between the other equation and this one, is we've actually combined the two masses together because they're going to travel as one object. Okay? So if, so I don't know, if you know, like when the dog comes jumping up into your arms, you add the masses of the two objects together to find the final velocity. Okay? Does that make sense? I hope so. I hope so. All right. So here's the formula. We just talked about that. Excuse me. All right. Let's give one of these a shot. Okay? I'm going to rewrite the formula up there on the top. So give me just a flash. M1 initial plus, oops, sorry, it's not a plus, it's a times. Velocity 1 initial mass 1 velocity 1 initial plus mass 2 velocity 2 initial is equal to mass 1 plus mass 2 times velocity final. Because the velocity of both you and your dog, if they jump up into your arm, are going to be the same. Okay? It's not like he jumps up, shoulder checks you, and knocks you out of the way. He jumps up into your arms. I hope he doesn't shoulder check you and knock you down. Okay, so here we go. Let's take a look at this real quick. It says a 1,500 kilogram car, so I have a mass 1 is 1,500 kilograms, is traveling at 15 meters per second, velocity 1 initial, 15 meters per second, to the south, collides with a 4,000, so mass 2 is 4,500 kilogram truck that is initially at rest. Velocity 2 initial is 0. Okay. The truck and the car stick together and move together after the collision. So that's where this piece is coming in. The two masses become one. Pretty nasty accident, it sounds like. Okay. What is the final velocity of the two vehicle mass? All right. So I need to find velocity final. Okay. All right. So let me go ahead and start filling this in. Mass 1, velocity 1. So I have 1,500 kilograms times velocity 1, 15 meters per second, plus, now just because of space, I'm going to go ahead and just do this out real quick, because it says it's at rest. That means velocity 2 is going to be 0. That means this entire term is going to be 0. Okay? And that's going to equal the mass, 1,500 kilograms, plus 4,500 kilograms, times velocity final. Okay? Tara! Go on. Okay, so 1,500 plus 4,500 times velocity final. Okay, and that's what I'm looking for there. Let me go ahead and do this real quick. Oh, goodness. 1,500 times 15. So that gives me 22,500. 22,500. Right? Yep. Kilogram meters per second. And that's going to be the total of that, because it's 0 there, is equal to, let's see, was it 6,000? 6,000 kilograms times velocity final. Now I just got to divide it through, divided by 6,000, and I get 3.75. And that's meters per second. Okay? All right. Let's try the second one. Let me get rid of all this. All right. A grocery shopper tosses a 9-kilogram bag of rice. Holy crap. 9 kilogram. Okay, so 9-kilogram bag of rice. That's mass of the mass 1 of rice. Into an 18-kilogram stationary cart. 18-kilogram stationary cart. That means this velocity initial for the cart is 0. It says it hits the cart with a horizontal speed of 5.5 meters per second. All right. And I need to find the final velocity, right? What is the final speed of the cart and the bag? All right, so here we go. Mass, once again, for this one here, the velocity is 0 because the cart is at rest. That means this entire term is going to be 0. Let's see, so I'll have 9 kilograms times 5.5 meters per second, meters per second, plus 0, that's my second term because of the 0 velocity, is equal to, let's see, 9 plus 18, that's going to give me 27 kilograms, velocity final. Okay? So this is just right out of the problem there. This was because of the fact that the velocity was 0. turning that entire term to 0. And this was the mass 1, 9, plus mass 2, 18. So that gave me my 27 right there. Okay? So now let me go ahead and solve this out. I had 9 times 5.5. That gives me 49.5 kilogram meters per second, plus 0, still get the same, is equal to 27 kilograms times my velocity final. And once again, I don't, delete. All right, and if I go ahead and divide this through, I end up with 1.8 meters per second. All right. Awesome. One more. Just one more. I know. The thing that sucks about this is you don't have the bell to get you out of doing more problems. Sorry, there's no bell saying we get to go to the next class. You're stuck. All right. The last problem, this one's actually cool because it actually doesn't have, I don't think it has the initial velocity of 0 for one of them. It's, yeah. All right. So let's see, we've got mass 1 is, it's a 47.4 kilograms. Student runs down the hallway, or the sidewalk, and jumps with a horizontal speed of 4.2. So velocity 1 initial is 4.2 meters per second. Onto a stationary skateboard. Oh, okay. The student and the skateboard move down the sidewalk with a speed of 3.95 meters per second. So my final velocity is 3.95 meters per second. I need to do two things. One, I need to find the mass of the skateboard. So I'm looking for M2. And, all right, let's do that first, then we'll get to the second part. Okay, so I'm looking for mass 2. All right, so it gives me this first part. It told me that the skateboard was stationary. Okay, I need to find mass 2. So let me go ahead, I'm going to do a little bit of math so I can save some board space. For this piece, 47.4 times 4, 47.4 times 4.2, I get 199.08. All right, kilogram meters per second. So that's this term. For this term, only thing I know so far is that the skateboard was stationary, meters per second. So I'm looking for that right there. I'm looking for mass 2. Okay, and it went ahead and told me that the final velocity was 3.95. Equals 47.4. I'm going to need to move that up. Equals 47.4 kilograms plus mass 2 times 3.95. End up doing first is distributing this 3.95 through here. So I'm going to have 47.4 times 3.95, and that's going to give me, let's see, 199.08 kilogram meters per second plus mass 2 times 0 meters per second. Is equal to 187.23 kilogram meters per second plus 3.95 M2. All right, so that gives me that so far. I'm going to go ahead and subtract this from both sides. 199.08 minus 187.23. That gives me 11.85 kilogram meters per second. All right. So what we need to do then is, now that we have it down to this point right here, 11.95, and that's just me taking the 187.23, moving it to the other side, and I ended up with 11.85 kilogram meters per second plus M2. And this 0 meters per second, it's really not adding anything. So I can go ahead and get rid of that. And if I go ahead and sorry, that gets rid of all of that. Sorry. Equals 3.95 M2. Divide both sides by the 3.95. That's going to give me 3 kilograms. And that's what I'm looking for. All right. And then the second part, how fast would the student have to jump to have a final speed of 5 meters per second? Okay. So let's see, it's 3. All right. So I know the mass, see mass 2 of the skateboard, I know that's 3.0 kilograms. That's going to make it a little bit easier for me. All right. But now it wants the final velocity. It's wanting the final velocity to be 5, I think. My tablet just died. So it's 5.0 meters per second. So I've got initial velocity for the skateboard, or for the skater. I've got initial velocity for the skater. The mass of that, and also I know the velocity initial of the skateboard was 0. Okay, so that means that this is going to be 0 here. M1 47.4 kilograms times the velocity, I don't know, plus 0, because that's going to be this business right here, this guy right here, with it being at rest, is going to equal the mass 1 plus mass 2. That's going to be 50.4. 47.4 plus the 3 gives me 50.4 kilograms times the velocity. They wanted 5.0 meters per second. Okay, so we have the final velocity needs to be 5.0 kilograms or meters per second. Okay, I need to find out how fast the skater is going to have to jump onto the skateboard in order to achieve that. Okay, so let's go ahead and I'm going to go ahead and do this real quick. 50 times 0.4, or 50.4 times 5. This gives me 252. So I'm going to have 47. Oh, the video camera went crazy on me all of a sudden, so I don't know if you saw all of the problem or not. But I wanted to go ahead and kind of take a step back. So hopefully I don't know how much is repeating. So we were talking about the skateboarder jumping onto the skateboard. We knew the skateboard was at rest, so it has 0 momentum here. We were looking for how fast the skateboarder had to jump onto the skateboard. So we went ahead. This just drops out. I just dropped it out right through here because it's 0, of course. And then 50.4 kilograms times 5. We got that at 252 kilogram meters per second. So we ended up with our final equation being 47.4 kilograms, the mass of the skateboarder, times his velocity, which we didn't know yet, is equal to 252 kilogram meters per second. The last step is just to get velocity initial by itself, divide both sides by the 47.4, and we end up with 5.31 meters per second. And that has to deal with elastic and inelastic collisions, all right? That's pretty much it for momentum. The formulas, just to make sure you have them, the formulas we have, there's the first one. This is the one for an inelastic collision. It's where they crash together and they travel off together, off on their own. The formula for conservation of momentum when the objects are elastic, where they don't stick together. M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. And then we had that force, this is the impulse momentum theorem. Force times change in time is equal to the change in, momentum, just like yo. And then we had just momentum is equal to velocity, or mass times velocity, same thing. Mass times velocity. All right. So those are the big equations that you have for this particular unit. Good luck. I am floating around, so if you have any questions about the calculations homework that I have for you guys, please don't hesitate to ask. When you're turning in your work, just take a picture of your work that you have, and then just you can turn that in, just a picture of your work. Make sure your answers are able to be seen, and also make sure that you have a real clear picture of it. If it's all blurry, it's real hard to read. So there we go. Good luck to you guys. I hope you guys are staying safe. If you need me for anything, don't hesitate to email me. Tuesdays and Thursdays I am online. I'm online pretty much every day, but Tuesdays and Thursdays I have my office hours from 10 to 2. Just check in Google Classroom for a link to the video conference. All right, guys, you have a good afternoon. I hope you're staying safe. Hope to see you really soon.